Hello everyone. In this topic, I'll be discussing about cosmology. What is cosmology? It is actually a branch of astronomy that involves the origin of the universe, from the Big Bang to today and into the future, typically understanding how the universe works. It is said the age of the universe is approximately 13.8 billion years. After the Big Bang, there are two eras, which is the radiation era and the matter era. So let's just enjoy watching the video on the birth of the cosmos.
The universe is everything, from the tiniest particles to the largest galaxies to the very existence of space, time, and life. But how did it all begin? The origin of the universe is the origin of everything. Multiple scientific theories, plus creation myths from around the world, have tried to explain its mysterious genesis. However, the most widely accepted explanation is the Big Bang Theory. The Big Bang Theory states that the universe began as a hot and infinitely dense point. Only a few millimeters wide, it was similar to a supercharged black hole. About 13.7 billion years ago, this tiny singularity violently exploded. And it is from this explosion, this bang, that all matter, energy, space, and time were created. What happened next were two major stages of the universe's evolution. Called the radiation and matter eras, they're defined by key events that helped shape the universe. First came the radiation era, named for the dominance of radiation right after the Big Bang. This era is made of smaller stages, called epochs, that occurred within the universe's first tens of thousands of years. The earliest is the Planck epoch. No matter existed in the universe at this time, only energy and the ancestor to the four forces of nature, the superforce. At the end of this stage, however, a key event occurred in which gravity split away from the superforce. Next came the Grand Unification epoch, named for the three remaining unified forces of nature. This epoch ended when one of those forces, called strong or strong nuclear, broke away. Then, the inflationary epoch began, during which the universe rapidly expanded. Almost instantly, it grew from the size of an atom to the size of a grapefruit. The universe at this time was piping hot, and it churned with electrons, quarks, and other particles. Then came the electroweak epoch, when the last two forces, electromagnetic and weak, finally split off. During the next stage, the quark epoch, all of the universe's ingredients were present. However, the universe was still too hot and dense for subatomic particles to form. Then, in the Hadron epoch, the universe cooled down enough for quarks to bind together and form protons and neutrons. In the lepton and nuclear epochs, the radiation era's last two stages, the protons and neutrons underwent a significant change. They fused and created nuclei. And in doing so, they created the first chemical element in the universe, helium. The universe's new ability to form elements, the building blocks of matter, cued the matter era. Much as the name suggests, the matter era is defined by the presence and predominance of matter in the universe. It features three epochs that span billions of years, the vast majority of the universe's lifespan, and includes the present day. The first was the atomic epoch. In this stage, the universe's temperature cooled down enough for electrons to attach to nuclei for the first time. Called recombination, this process helped create the universe's second element, hydrogen. This hydrogen, along with helium atoms, dotted the universe with atomic clouds. Within the clouds, small pockets of gas may have had enough gravity to cause atoms to collect. These clusters of atoms, formed during the galactic epoch, became the seedlings of galaxies. Nestled inside those galaxies, stars began to form. And in doing so, they cued the latest and current stage of the universe's development, the stellar epoch. The formation of stars then caused a tremendous ripple effect and helped shape the universe as we know it. Heat within the stars caused the conversion of helium and hydrogen into almost all the remaining elements in the universe. In turn, those elements became the building blocks for planets, moons, life, everything we see today.
The universe is expanding, as what Edwin Hubble observed in his telescope. He was able to see the movement of the galaxies going far away from Earth. So this movement of galaxy, they actually name it Hubble Constant, or also known as Hubble Lemaitre law. Hubble constant is the observation in physical cosmology that galaxies are moving away from Earth at velocities proportional to their distance. So velocity is actually measured using a redshift and proportional to its distance. In other words, the farther they are, the faster they are moving away from the Earth. And here is a picture of radiation. So this is actually a map of radiation of the universe. The red color here is actually higher dense and it's very hot. And the blue ones are the cool, where the matter actually combines. And here's another picture, the same picture. And this is actually called a cosmic microwave background, or CMB. Hubble constant, also known as H null. So this is the other name for Hubble constant. And the formula for a Hubble constant is H null equals to velocity over distance. Okay, we described earlier it's proportional to its velocity and the distance. And there are actually three values for Hubble constant, which is being debated until now. But this last value is actually just discovered recently. This one, the first one, is using the cosmic microwave background, the one that earlier, the picture. It values as 67.8 kilometers per second. So kilometers per second is our velocity. And this one is megaparsec. Parsec is actually a measure of distance. The distance is very long, so that's why they name it as parsec. Measuring the distance in the galaxies or in the universe, they actually use the parsec. So using the cosmic microwave background. Next one is 73.24 kilometers per second per megaparsec. And this measurement uses the cosmic distance ladder. So there will be a video after this and you will understand how the cosmic distance ladder work. And finally, the most recent one discovered by the scientists when they measured the gravitational wave. LIGO stands for Light Interferometer Gravitational Wave Observatory. So they actually have a observatory with lasers on it. So using those lasers, they can actually detect the gravitational wave. And they are actually excited to detect this because they have proven the theory of Einstein. And measurement or the value for Hubble constant is being recognized as this one.
Ever since Edwin Hubble discovered that the universe is expanding, there's been a great debate about the speed of its expansion, also called the Hubble Constant. In 2000, scientists thought they had reached a consensus, with the Hubble Constant at about 72. But since then, two methods of calculating the expansion rate have gotten farther and farther apart, and some scientists think it's too big of a difference to just be a statistical fluke. To calculate the Hubble constant, we need both a velocity and a distance. Velocities are easy. It requires measuring the redshift of a galaxy as it recedes. But distances are much harder. We need standard candles, objects that shine with an intrinsic brightness. That way, its observed brightness could be converted to a distance. The first method used to calculate the Hubble constant originated with Hubble himself. He started by measuring distances to nearby objects and working his way out, hence the name, the cosmic distance ladder. The first rung is within our Milky Way. Here we measure the distances to Cepheids, pulsating stars that have an intrinsic brightness. Then we look to nearby galaxies that contain both Cepheids and another type of standard candle, Type 1a supernovae. These exploding white dwarf stars also have an intrinsic brightness. After calibrating these supernovae, astronomers can then move out to a third rung, to even more distant galaxies that only contain supernovae. Linking all these measurements, a recent study has pinned the Hubble constant at 73. Instead of starting within our galaxy and looking out, the second method looks back in time to almost the beginning of the universe. Here we find the cosmic microwave background, the radiation left over from the Big Bang. The CMB's subtle variations in temperature describe changes in the density of the universe right after the Big Bang. Instead of standard candles, physicists use the size of the tiny fluctuations as standard yardsticks. With these yardsticks, they can calculate what the Hubble constant would be today. Recent estimates are at about 68, significantly lower than the cosmic distance ladder's approach. Both camps hope to resolve this debate in the coming years with the help of new telescopes and instruments. But if the discrepancy in the Hubble constant remains, it could mean that our understanding of the expansion of the universe is missing an ingredient. That something happened between the Big Bang and the present. Maybe there's a neutrino out there we haven't discovered. Maybe the mysterious force, dark energy, which makes up a significant portion of our universe, can change in strength. Or maybe subtle flaws in one or both approaches to the Hubble constant are giving us the wrong answer.